otherwise arbitraging their transactions. So in this very new context, programmable privacy refers to the ability to arbitrarily specify the conditions on which you reveal or not reveal some confidential information. And I think what's interesting to note here is this sort of privacy is very instantaneous. So in this context, they are referring to pre-trade privacy, whereby, yeah, you don't want to reveal the information before you're guaranteed some share of the profit. However, you do want to execute the trade eventually. And so in this context, you want to reveal the information, and quite soon, in fact, before the block epoch is up. And there's been discourse recently as well about the usefulness of pre-trade privacy in isolation, or in other words, does revealing this trade after execution negate any of the benefits gained from concealing it before? So really, it's an active and very exciting area of research. There's lots of money at stake, and the people at Flashbots are realizing how strategic privacy can help to protect users and can help users to retain more value in the protocol. And for the rest of us who have been working in privacy-centric projects such as Zcash or Secret Network, we have a slightly different understanding of this same phrase, programmable privacy. Here, we never want to reveal the information. So it's not instantaneous privacy, it's privacy forever. But we are interested in the scope or the range of computation that we can perform on this concealed information. So for instance, Secret Network, they have a network of trusted execution environment nodes that users encrypt to, and that are responsible for performing arbitrary computations on this encrypted data. And furthermore, we may be interested in verifying arbitrary features of this concealed data. So programmability here does not come in when revealing the data. We never reveal it. Rather, it comes in when making computations or making statements about this concealed data.
So really, when we talk about programmable privacy, we're really talking about that kind of layer of like application design, right? Like when we think about zero knowledge and being able to program circuits and program applications, we are always like considering the whole stack from, is our proving system generic enough to hold sort of any kind of statement in the circuit? Do we have kind of a language like a ZKVM or some type of API that allows us to write circuits in a generic way? And then we're talking about this idea of, do we have a protocol that can allow for others, essentially other developers, to build some kind of application on this protocol, right? So in this case, Zcash is not programmable, but there is like specific functionality in for using applications. That's one of the things that Kedit is doing. This is also an example like for Tornado Cash, for example, where the application is really to just have kind of a mixer, a private transfer application on Ethereum. But it's also like Nocturne, where essentially it acts as a kind of proxy party to allow users to interact privately with other smart contracts, right? And then we have a kind of protocols. So the idea that the protocols that I was mentioning have this application privacy. Basically, they can offer, the specific projects can offer and need to have this kind of responsibility to make sure that there is sort of anonymity sets in the applications, but also like to be able to potentially build kind of a larger anonymity set of some sort. So this is an example from Namada that this is one of their goals, right? To build kind of a anonymity set for assets on Ethereum and across actually other chains. Another kind of thing that can be done or given in the support of these protocols is enabling unlinkability of actions on chain, like Zcash and Zerocash kind of built this idea of unlinkability by doing kind of commit and nullify and whatnot. And for example, the Aztec protocol or Aztec 3 has been now thinking about how to expand that to larger kind of sets of computations. Zexi does that as well in some way. Another one is really to providing economic security guarantees, right? So all these assets are now dependent on the kind of protocol and the cryptography, so not only for the privacy, but also for the security. We have that we want to encourage users to have like a privacy preserving design, and sort of this comes down to kind of the way that the protocol is also being designed specifically. If you give too much freedom, then there's a risk to have like less security or less privacy at the level of application. There is some protocols that do private and public, others that only do private, etc. And with that comes also the responsibility to kind of give an API that is ensuring some type of security, right? Like if you allow for like too much modularity, then it can break down differently. Yeah.
So hopefully that contextualizes and motivates this SOK. How we're going to proceed now is, first of all, we're going to introduce a high-level mental model, which we use to think about a range of protocols and applications covered in this SOK, which we'll enumerate. And then afterwards, we'll move on to really a Zcash specific part, our proposals for adjustments that we can make to the Zcash protocol to integrate these. And lastly, future work that we have planned. So yeah, first of all, the high-level framework. We conceptualize the protocol as consisting of two components. Firstly, a state that we can read and write. And secondly, a set of validity predicates that encumber or restrict how participants in the protocol read or write, or which subset of participants can read and which subset can write. So to make this more concrete, public state is defined as parts of the state that anyone can read, so there's no need to fulfill any validity predicate. Whereas private state is parts of the state that are actually restricted access. So you can think of this as a viewing key on Zcash, for example. Only those in possession of it can read or decrypt a certain note. And in practice, the point of an application and the point of having validity predicates is to encumber the rights, and it's to define what is a valid state transition or not. But what might be interesting to note is that when it comes to private state, reads and writes need not be encumbered by exactly the same predicates. For example, in Zcash, the viewing key versus spending key. And for example, in Penumbra, which we'll see later, writes are actually doable on-chain, even without the ability to read. So this framework is going to inform our classification of applications and protocols to follow. And mainly we'll be looking at two types of private rights. We found this to be the most interesting sort of split between these applications and protocols. So some of them do the private rights on-chain, and most of them do them off-chain. So the most familiar class of applications would probably be those that do rights, private rights off-chain. And in these applications, in many cases, private state is owned by a single user. So Zcash is an example of such an application where one user owns a note and is able off-chain to authorize the spending of said note. and reveals on-chain only some commitment to the node. And there is no mutation of this private state on-chain. Rather, there is just a verification of certain features of this private state. So really with this primitive, we can instantiate this primitive, this class of applications using just one primitive, which is zero-knowledge proofs. And we've been able to do a lot with this one primitive and with this one class of applications. So for example, I'll just fast forward here, but basically we have applications that provide functional privacy. For example, if you have a proprietary machine learning model that you want to prove is optimal on certain sets of inputs and outputs, you can provide the weights of your model as private input to some circuit, zero-knowledge circuit, for example. And you can do this because you, the user, know the entire private state, which is the weights of the model. So, and this, in the same spirit, if you have some kind of exploit that violates some invariant, you can prove the effectiveness of this exploit without having to reveal it. Same story with a bespoke trading strategy, attested sensors. Oh, yeah, I don't know what that one's about. Sorry, I made these slides, but I forgot what exactly that's about. The other large class of private application, off-chain private state applications focus more on data privacy. So in one primitive that appears everywhere is anonymity sets. And this is what offers confidentiality in Zcash, in mixers such as Tornado Cash. And it's what offers anonymity in identity systems. And this has been used to build anonymous reputation systems, which can just be layered on top as additional functionality. Anti-collusion voting as well is instantiable with just anonymity sets. And the last kind of data privacy really makes use of well-known public programs. So for example, like the DKIM signature and email protocols. Some people built ZK email verifying this. So the point is to conceal some parts of your email, but to reveal that you have like an email address from MIT or some reputable organization. And the same thing with standards like JSON, JWT, the TLS handshake. People have built circuits that are kind of Web2 oracles that encode the very well-known rules of these public protocols, but obfuscate private inputs. Yeah, and you could do the same with, for example, private inputs to a well-known public machine learning model. And you can use this for secret information games, as well as an interesting use case is proving that you encrypted something correctly. And this actually is necessary in some systems that we'll see later on that make use of FHE and that deal with ciphertext, but still need some proof of correct encryption of these ciphertext. So yeah, this is just like an incomplete taxonomy of the range of things we can do with just zero knowledge proofs, with just a single user knowing all the state and mutating it off-chain. And Zcash is one of these applications. Most interesting applications of zero knowledge proofs fall into this category. So for protocols to support these applications and to enhance their privacy, they need to basically compose anonymity sets across these applications. So for example, in the Zcash protocol, each application produces some state commitment that is indistinguishable from those of other applications. And therefore, by participating in the Zcash protocol, you're benefiting from the anonymity sets of state updates produced by all other applications in the same protocol. I will note that I think Alio, the project, removed this functional privacy from their implementation, but the original Zcash paper did have it and did allow composition of anonymity sets across applications. So, and as Daniel mentioned just now, Nocturne is an instantiation of this system on Ethereum. So Nocturne allows users to interact with arbitrary third-party smart contracts, such as Uniswap, from a single shielded pool. So basically, all interactions on-chain look like they're coming from the same shielded pool. And so it's a really elegant design because they don't conceal the actual actions that the users are taking, rather they just conceal the identity of the user. And this is sufficient, or this is the best we can do in many trading use cases, whereby we can, in fact, reverse engineer private trades just from looking at public price changes. So in those cases, there is no point trying to conceal the actual trade amounts. And the best we can do is to conceal the identity of the trader and prevent someone from inferring some kind of strategy or belief that is specific to one identifiable user. So the next class of off-chain private state applications actually support multi-user private state. And this is not ontologically different from the first class because, yeah, these modifications are not on the protocol layer, they're on the application layer. So basically, you can do, for example, some kind of MPC protocol to collaboratively form a transaction before submitting that transaction on-chain. So Flashbots did this experiment whereby they had a user submit some confidential transaction, and they had a searcher submit a confidential search algorithm, and they jointly computed a back-running transaction using the MPC protocol. And the idea here is that if they are successful in producing a profitable back-running transaction, then this transaction can be posted on-chain. And if not, then neither of them reveals their private inputs in the first place. So this is, so again, this transaction was formed using MPC, but to the protocol, it makes no difference how you form the transaction. So really this difference is on an application level. And besides MPC, another way we can achieve this is using collaborative ZK snarks. Actually, this is also just MPC. So this is when the parties in the MPC collaborate to compute a ZK proof, right? So the program that they're computing is the prover in your proof system. And the point here is that each party owns a different part of the witness, and working together, they can compute a proof attesting to the fact that this witness is satisfying. So the way protocols can support applications with multi-user private state is, I think Anoma is a good example of this. So I guess just focus on the leftmost part of the diagram. And this is when you see the idea of intent or partial transactions being sort of first-class citizens in the Anoma protocol. So they're all about defining some language to express general intent. And the point of these intents is that can be submitted to these parties called solvers who run some kind of optimal algorithm to match partial transactions and produce fully formed transactions. And often these partial transactions are atomic in nature, meaning either both parties are happy or like neither is happy, like nothing happens, I mean. And Aztec is another example of supporting off-chain private state.
Yeah, in Aztec, the point in a way is that they aimed for kind of very general programmability, in the same style than like Zero Cash introduced with commitments and nullifiers. In that way, what they enable is being able to have like a generic kind of note that includes information about any type of application. And then every time there is a read from that note, there needs to be a nullification in order to preserve the unlinkability. Now they have these sort of private functions and public functions. Now the private functions are associated each with sort of a specific circuit. And the way that this is verified on chain is that every proof is then verified at the consensus level. So it's still kind of off-chain computation. And there is like this kind of distinction between private and public functions in that first you want to do the private ones because you can access kind of historic reads. So just like in Zcash, you can span the note using a root of a commitment tree that is like older than the latest state. So similar to what that happens also in Aztec. But when you go into, and then of course the private functions can generate public state and whatnot, but then the public state always needs to be done based on the latest state of the chain. And this enables sort of full programmability from like a smart contract perspective.
So the next class of applications actually moves the computation of private state on chain. So I'm like by these two diagrams, I'm trying to illustrate the shift in that vertical bar, whereby in the off-chain case, this combination of private state is done off-chain, whereas in this new class of applications, it's done on-chain. So let's make it concrete with an example, Penumbra, for instance. It allows users to submit individual swaps that are in and of themselves not complete transactions. So what these users do, their private state is the swap. What they do is they encrypt it to some threshold of validators in the Penumbra network. Okay, and then what the protocol does on-chain is homomorphically sum up these encrypted swaps. And then threshold decrypt the aggregate swap. And it is this aggregate swap that is executed against some global liquidity pool. So the point here is that each individual swap is sort of concealed inside this batch. And yeah, what's different about ANOMA is that this sort of computation on private state is done on-chain. It's done blindly on a ciphertext. And yeah, by saying it's done on-chain, I mean that every consensus node in the network can do it, as opposed to previously when we were, I don't know, back-running things or when we were solving intents. All that was done off-chain by individual entities working together. So
one good example maybe is the kind of blinding signature on Zcash, right? Like there is still some kind of like on-chain action of adding some ciphertext or some like commitments, homomorphic commitments, but we still call that off-chain because actually kind of the result of the execution is already known off-chain versus in Penumbra where like the aggregation of these swaps actually gives a concrete result that wasn't known previously.
Yeah, exactly. So each user actually needs the help of the protocol actors to combine their traits with those of other users to produce the final batch swap that will be executed. So I hope this difference is clear. To me, this was one of the most interesting differences. And so using this primitive of like threshold, like additively homomorphic threshold encryption, I think they call this flow encryption. So using this primitive, Penumbra can implement batch swaps, voting in proof of stake, I think, and delegation in proof of stake. So anything that you can just add up and batch. So there's this project called Zama. They work on FHE, and you can think of it as just a generalization of Penumbra. So instead of additively homomorphic encryption, Zama allows us to do fully homomorphic encryption. Once again, it's to a threshold of validators, Zama validators. But the idea is the same as Penumbra. And another instantiation of this is a very recent Suave chain. So again, this is from the Flashbots project. And the idea is, so if you saw previously this back-running solving activity, it was previously happening off-chain. So the idea with Suave chain is they want to move these searchers and solvers on-chain. And how they do that is they encourage searchers and solvers to publish their strategies as smart contracts. And these smart contracts are deployed to what's called the MEVM. So it's like an EVM, but with precompiles that make searchers efficient. And these are deployed to, I think, their initial rollout is just deployed to like some centralized node, but eventually they want to deploy it to a TEE. And so this TEE holds all these private search strategies, and users can now encrypt their transactions and their bits to this same TEE, which will then use this information to form full transactions and full blocks. So the output of Suave chain is actually blocks that will then be submitted to the Ethereum chain. But I consider this on-chain because the Suave protocol is responsible as a whole for running, for mutating private state. And Secret Network sort of generalizes this to not just searchers and solvers, but to any smart contract. But the idea is the same as Suave chain. So Secret Network has a network of TEEs. So each of the nodes in Secret Network is a TEE.
Thank you. So we just went over sort of all these applications that we've been exploring, the protocols. You saw that we didn't leave aside kind of any specific technology, like we included homomorphic encryption, we are considering TEs as trusted executed environments, and of course zero knowledge, right? Because we understand that the path of the future for programmability is not purely in zero knowledge, because that could potentially constrict also the type of computations. So we're going to explore a few of the ways that we believe that Zcash could include programmability. Now, there are many ways, so if we don't cover all the details right now, I mean, this is fine. We still haven't formed like a very deep opinion or strong opinion ourselves, so we're still working on this. But the first sort of direction that has been thought of before as well is the Zexy style, right? Like if we could generalize the type of nodes inside of the Zcash protocol to include more than just the asset value, the asset owner, and of course the details specific to security, this could allow for Zexy, where basically there is kind of a payload, like you could think about it as a fixed memo that needs to include some kind of like proof of validation of some external application, right? That's why this is still like on the off-chain kind of realm. And we started with Zexy actually because So the order here is kind of in order of invasiveness in a way, like how much do we need to change the protocol? You may have differing opinions. We're definitely open to discuss this more in detail at the conference and otherwise. But the good thing about Zex is that the kind of type of protocol would be preserved, right? It's still like a commitment, and there's nullification, and transactions could look similar to what it is today, which also includes like the impact to the users, right? Like we also need to be wary of how much the protocol changes and the usability of Zcash, because as Zuko mentioned here, like it's not only about the protocol. There is UX, there is applications, there is miners, etc. Then we have the idea of TEs, right? So in this case, I don't know if I can, oh, this is cool. So if we consider these blocks like the Zcash network as like the blockchain, adding TEs would be quote unquote relatively simple. And of course, I don't want to ever say simple in reality when it comes to cryptography, but it basically would mean sort of sending some kind of off-chain data that basically would still have to be included in the network itself, in the protocol, as like specific to TE. But then like all of the computation of the applications would be done inside of this hardware environment. And then some kind of signature is being sent back that needs to be verified at the consensus level. So these two changes are seemingly like, or relatively, I don't want to be simple.
So yeah, and thank you to Andrew Miller. I just stole this diagram from his slides. He's been talking about this tea kettles. Basically, they are this overlay network of TEEs, but they do derive some security from the layer 1 Zcash in the sense that messages encrypted to these TEEs are publicly committed to in layer 1 Zcash, and that's how we force inclusion into this overlay network. So yeah, I agree that this is a relatively light change because, I mean, it's just about interpreting the public messages on Zcash.
Mm. Yeah.
Right, and so this is another idea that I stole from the ANOMA team. For a privacy-preserving bridge. Well, the idea here is to not introduce that much programmability on Zcash, but rather to introduce a privacy-preserving bridge to, let's say, ANOMA or some other protocol that does have native programmability. And we like this idea because, yeah, all you're changing on Zcash is the ability to support a bridge. And you're sort of delegating the actual programmability to, say, ANOMA. So, however, this is still an invasive change because a secure privacy-preserving bridge requires the introduction of some threshold validator set, and we're gonna see why. So, we're gonna take it in both directions. The first direction is, let's say, going from Zcash to ANOMA. So over here, the user basically spends their note to the escrow address, and they encrypt the value of the note to this threshold of validators that we've introduced. Now, ANOMA is running a Zcash Lite client, and is watching for the inclusion of notes meant for their chain. So when they see a new note commitment, and they validate that Zcash consensus has agreed on this commitment, ANOMA proceeds to mint this note on their chain. And so now anyone who knows the note plaintext can spend it on ANOMA now. So this direction is pretty simple. It's the other direction that is trickier. So look, we're on ANOMA, and they have exchanges. They have like NFTs and all kinds of weird and wonderful things. So we're spending our wrapped Zec arbitrarily and freely. And then at some point, maybe some subset of wrapped Zec owners on ANOMA decide they want to go back to the Zcash chain. They want to cash out. So what they do is they burn these wrapped Zec to the mint and burn contract. And once again, they encrypt the values of these notes to the threshold of validators. And by the threshold of validators, I mean those on Zcash. And then the Zcash chain is also running an Anoma Lite client. And once they're convinced of the inclusion of these burnt notes, what they're gonna do is, and here's why we need the threshold validators. What they're gonna do is check that this invariant is conserved. So they're gonna check that the amount burnt on Anoma does not exceed the amount escrowed on Zcash. And this guards against the situation where, let's say, the foreign chain becomes Byzantine and tries to increase the Zcash supply using this bridge. So we can never sort of burn more money than we have, even across chains. That's the point of this threshold encryption, is to check this invariant in a privacy-preserving way. So once this check passes, then Zcash mints these notes, and whoever knew the note commitments on the note plaintext on Anoma can now spend them on Zcash. So this is, by the way, my understanding of what Anoma described, and all mistakes are mine.
So I just wanted to add that there is like two other ways. I think maybe we changed the slides a bit too late, but there's like another direction that is basically the direction that Kedit is taking right now, which is to add like specific functionality, right? Like we have this vision or ideal that, we want to add programmability because we want to code everything and be able to do any application. But that has two real like challenges that I don't think we've solved yet. One is that first, we maybe don't need all types of applications or all types of programmability on chain. And two is that actually we are giving maybe too much freedom for the developers to build something that they don't really know if it's secure. Whereas when we do this in a kind of more, let's say, proactive approach by adding specific functionality, and of course it can take a while, but let's say like in a few years we can have the major kind of DeFi components on Zcash. Well, that seems pretty much like pretty good to have like a good user base. At the end of the day, how much more has been done in Ethereum that actually created adoption, right? Like, okay, games and stuff. Let's put that aside for a second. And the other direction is kind of what Aztec was doing, which is like do the on-chain kind of execution, have like the specific programmability be part of the consensus itself. So those are like two other ways. Those definitely are like more intense and work intense and will change the protocol a lot more. And in terms of future work, so first of all, of course, like we're still in the middle of this project. We're now hoping to kind of crystallize certain aspects. This is kind of an initial kind of table of contents for the actual paper. Our goal is to publish this work. We want to really focus on formalizing privacy and security definitions, because this is, I think, one of the benefits of having a type of SOK work where you can actually like formalize things that then can be continually used afterwards, right? Like so far, let's say that like most of these protocols that we've spoken of today, I would dare to even say all, don't have a proof of security as a protocol, right? So, okay, so maybe that's too much to ask in some cases. I feel like we're advancing too fast in these, like very fast in this industry, so that like we can allow ourselves to not be super, fine-grained with the security proofs. But having specific security definitions would help all of these protocols to kind of map these security definitions into the protocols. And similar with privacy. Some people are talking about, ledger indistinguishability. Others are talking about unlinkability. Others are talking about, etc. So we really want to try to formalize these things, and it's really difficult. So
yeah, our colleague Brian has been looking into universal composability because basically lots of these protocols involve parts beyond just the ideal functionality. And so to try and capture it meaningfully, we might need to go beyond those very theoretical definitions in, say, zero cache paper.
Yeah. We're also thinking about kind of what are the common classes of privacy-preserving applications. So today we presented kind of the framework and what are some examples of these applications, but really what we want to try is to kind of understand what are the meaningful differences between the applications that create an extra need for functionality at the protocol level, right? Like, for example, right, Zcash can now support, let's say, ZSA, but it cannot support swaps because that's an extra functionality, right? So in the context of programmability, that also exists in some contexts. Like penumbra is also not fully programmable, right? So we're aware of those, and we want to kind of try to pinpoint them. And also sort of what are the best practices for designing these, right? And here it's kind of similar, right? Like what are the minimal protocol level primitives needed, right? So can we like bring down all these functionalities to the essential kind of functionalities and primitives? And can we actually implement those well and audited and in a secure way so that we can help ensure the user or developer's application security? Yeah, so that's for now. Hopefully we'll have more to present soon. Any questions?
Oh, how can we make programmable Zcash secure against basically hardware level attacks?
Against code exploits and processor memory disclosure attacks.
Against code exploits and processor memory disclosure attacks.
I'm not sure. I think like we're not too, like we're still a bit far from getting again from this opinion on how to make it work. I think like from code exploits, it's really difficult to. I think it's also a little bit perpendicular, to be honest. It's not clear.
I think we could best answer this question relative to a specific proposal for integrating programmable privacy, and we provided a few in pretty much ascending order of invasiveness, and I think each of these, introduces additional security assumptions to an extent. So if you add Zaxi like arbitrary functionality, then you're allowing users to, for example, create trivially de-anonymizing programs. You could absolutely do that. You could make zero knowledge proofs for like a fundamentally de-anonymizing program. For example, in this TEE case, you have lots of side channels that can happen on TEEs, but you could find ways to mitigate this. For example, Andrew Miller suggested using FHE as a primitive and using TEE just for the threshold encryption part. So have each TEE node hold one share of the encryption key. And so this sort of defense in depth, like reducing our reliance on security assumptions that we don't understand, I think is generally the strategy that will win out and that will provide security, even when we introduce like fancier types of programmability. And when it comes to bridges, it's like a whole nother game. It's like economics, for example, considering the probability of the other chain becoming Byzantine, considering like the value of the native assets on each chain, considering like smart contract bugs on the other chain. So in short, we don't know, and we could probably answer this better offline and in relation to a specific proposal.
Great. Well, we're out of time, so thank you very much, Ying Tong and Daniel.
Thank you.
And we'll be back in 7 minutes with Kartik Nayak from Duke University, who's going to be talking about privacy, preserving proof of stake, and what the trade-offs are with regards to safety, liveness, and privacy. So we'll see you then. 7 minutes, please. Please be on time.